Okay, this first problem from chapter 13 deals with predicting relative solubilities. So to keep this problem really simple, all we need to say is like dissolves like. I'll talk in a second about what that really means, but if you have a very polar solute, you want to pick the most polar solvent. Conversely, if you have a solute that has a little bit more of a nonpolar character, you want to pick a solvent that matches that. Okay, very briefly just to talk about why that is, they talk about it in the problem here. A solute is going to be more soluble in a solvent whose intermolecular forces are similar to and therefore can replace its own. So remember, when we talked about in class today, what it really means when we dissolve something is you have to break interactions between solute and solute, solvent and solvent. That's always a cost. And then we make new interactions when solute and solvent come together. And it's really a cost-benefit analysis about how much did it cost to break those and how much do you gain when you make new interactions. Well, if you have two things that are not like one another that come together to try to form new interactions, they're not going to form very strong intermolecular forces. And so that gain won't be very great, but you'll still have the cost of breaking interactions that were favorable. Okay, that being said, let's go through this problem, and it's fairly simple to think about. If we just apply the like dissolves like, and we ask about the polarity of our solute and pick the solvent that has the most similar polarity. Okay, so for the first problem, we're considering sodium chloride. Remember, sodium chloride is an ionic compound. So when it dissolves, or because it's an ionic compound, dissociates, we make sodium cations and chloride anions. This is a very polar situation. So polar that we actually have the extreme of a complete electron going to chlorine and an electron being removed from sodium when you make this ionic compound. So that being said, we'd like to pick the most polar solvent. So the two solvents that we have to choose from are methanol and 1-propanol. So again, if we look at our intermolecular forces that are kind of available in between these, because those are what are going to need to be disrupted when we break these, we actually have the same between all of these, right? We've got London dispersion forces, dipole-dipole interactions, and hydrogen bonding. So that's not really going to give us a difference. And if we look at trying to figure out which is more polar, propanol has a much larger hydrocarbon portion to it. So again, these are some of these molecules that we said have dual polarity. And so in this case, we're going to have a much more polar substance if we choose methanol. So methanol is going to be the solvent of choice here. Okay, now the second problem here, ethylene glycol. So ethylene glycol is a alcohol that actually has two alcohol functional groups there. So ethylene glycol has two alcohols, and we have to choose either hexane here or water. And in this case, we can see these two solvents are very different. Hexane, for example, is a purely nonpolar solvent, and water, as we know, is pretty much the extreme of a polar solvent. So because we have a fairly good amount of polar character to ethylene glycol, for this case, we also would like to choose water. Now lastly, diethyl ether. This one's a little bit challenging because we're given water or ethanol, and we would consider these to both be polar solvents. However, if we look at our solute, in this case having diethyl ether, yes, has some polar character to it, but it also has a significant amount of nonpolar character here. So in this case, we don't want to pick the extreme of a polar solvent and picking water, but we'd like to pick something that allows us to play to both the polar and nonpolar characters of this solute. So we're going to pick ethanol.